Hi, this is the ninth part of the series, and we're going to be looking at algebra. Now, there's different types of algebra out there, quite a lot of them, but we're going to be looking at just the very basic one, generally called elementary algebra. This is the kind of algebra we're most familiar with in our day-to-day lives. The name, algebra, is based on a 9th century book by a chap called Al-Khwarizmi. Apologies for pronunciation. Same guy who invented algorithms, and I'm guessing a bunch of other things starting with Al. So many parts of algebra have equivalents in programming, such as constants. A constant is a number value that doesn't change. That doesn't necessarily always mean that you know what the value of the constant actually is. It may be an unknown constant. Typically, they're called C or K in an equation, but not always. In fact, we'll see maybe a few that aren't over the course of the next few videos. And in programming, constants can take up pretty much any name, so you should avoid letters like C or K unless that's just what they're actually called. Constants could be called something like, number of bad guys or whatever. Alternatively, there's variables. Variables are numbers which can change or vary, hence the name. The current value of a variable can be known or unknown, at least in maths, not so much in programming. A lot of maths revolves around finding the value of an unknown variable. And in maths, these variables are usually given single letter names like x or y. Again, in programming, you should try and strive for more meaningful names like score or lives. And of course, as I said a moment ago, in programming, values of the variables must be known. If you need to calculate an unknown value, then you'll need to make a temporary variable to put it in until you know the right value. Then we've got coefficients. A coefficient is just a number that you multiply a variable by. For example, if you've got a term 3x, then the variable is x and the coefficient is 3 because that's what you multiply the variable by. And the coefficient itself can be a variable or a constant. Like, for instance, in one of the most famous equations, y equals mx plus c. X is obviously the variable. The coefficient is m, which is itself a variable, which may have a known or unknown value, depending on the situation. Next up, we've got exponents, or orders, or powers, whatever you want to call them. An exponent tells us to repeatedly multiply a variable by itself. The value of the exponent tells us how many times the variable appears in this multiplication. For example, if you say y squared, that means there's two lots of y that appear, y times y. If you see 10 to the power 4, that means take number 10 and do a multiplication with that number appearing 4 times. 10 times 10 times 10 times 10. 4 of them. You get 10,000. It also just so happens when you do 10 to the power something, it tells you how many zeros, the power tells you how many zeros there are. But that's by the by. If you see any value to the power of 1, that means the x value appears once in the multiplication. So in other words, it's just x. In fact, that's true of anything to the power 1. 5 to the power 1 is 5. There are special rules for exponents of 0 or lower, or fractional exponents. We'll see them shortly. But next up, we've got operators and operands. An operator is a symbol for some kind of maths operation, like the plus symbol, multiplication, or factorial. Now, some of these are what we call unary, and a unary operator means that the operator just takes one number as an argument, or parameter, whatever you want to call it. So there's the number minus 90. This is not a subtraction operation, it's the negation or negative value. So that takes a single value, in this case 90, and negates it. 5 factorial takes a single value and performs an operation. They're both unary operators. You can have binary operators. This takes two values, for example 3 plus 5, 20 times 4. Don't confuse it with binary numbering systems, which are just values of 0 and 1, or the base 2 in other words. That is a different thing. Binary as a word just means composed of two things. So that, like an operator that is binary is composed of two operands. A base numbering system that's binary is composed of two symbols, 0 and 1. But you can have loads of other things. You can have, binary explosives, mix two things together and it blows up, and so on. There's also terms and expressions. You should be aware of these words. An expression is a combination of mathematical operations. It may go on one side of an equation or formula. In algebra, it's usually made up of multiple terms. So the terms are things that get added together. If you're multiplying or dividing or doing factorials, that's not a term. If you add them together, they are terms. And when you add the terms together, you're evaluating the expression, and that works out the answer. Terms can include numbers, constants, variables, coefficients, exponents, and unary operators, all the stuff we've just seen. For example, 5x cubed plus 3x squared plus 5, that's an expression. There's three terms here, 5, 3x squared, and 5x cubed. You've got operators, you've got operands for those operators, you've got powers, you've got coefficients, you've got variables, and you've got a constant. It's all there, it all lines up. You may well be aware of these things, but might not have known all the terminology for them. So there you go. Reciprocal of a number is whatever you have to multiply it by to get back to the value of 1. In other words, a number multiplied by its reciprocal is equal to 1. This is also called the multiplicative inverse. We'll see other inverses shortly, but a multiplicative inverse means you multiply something by something else and get 1. For example, 2 has a reciprocal of a half, because if you multiply them together, you get 1. Take a more detailed example, 4 divided by b. If you multiply that by b divided by 4, then you get 4b on top, you get 4b on the bottom, which cancel out, and you get 1. These are multiplicative inverses, and in fact, that's how you can use that trick to cancel terms out sometimes. Now, inverse operations in general, just like a multiplicative inverse cancels out another number, an inverse operation sort of cancels out another operation. If you start with a number and do one operation, and then do the inverse, you get back to what you started with. So if you add and then subtract something, for example, x, take x, add y, but then subtract y, you get back to x. If you take x and subtract y, but then add y back on, you get x. Multiplication and division are inverses. If you multiply by something and then divide by it, you get back to the number you started with. X squared is the inverse of the square root symbol. Now notice this square root is also happens to be x to the power of a half. I did mention we'll look at fractional exponents shortly. X to the power x to the power of a half is a square root because it's something you're finding the number you have to multiply by itself. So it appears twice in the equation. X to the power 3 has the inverse of the cube root of x, or x to the power of a third. You're looking for the number that you have to multiply by itself, which appears 3 times in the equation to get that. And you can carry that on to the x to the power 4, x to the power 5, 6, whatever. X to the power n, the inverse is the nth root. So for example, if you've got a square root of x squared, and that cancels out. But another way of looking at that is that we're looking at x squared and then to the power of a half. The 2 and a half are multiplied together to get x to the power of 1. We'll see why in a sec. But yeah, that gives you x to the power 1, which is, as we saw a minute ago, is just x. Same with cube root of x cubed. The cubes and the cube roots cancel out. You're left with x. Nth root and nth exponent cancel out. So these are all inverses. Just a few examples. There's loads more out there. But moving on, we're going to look at the laws of exponents. So the first law is the product rule when two variables have the same base. So x to the power a times x to the power b gives you x to the power a plus b. For example, 3 squared times 3 cubed. So 3 squared means there's 2 3's. 3 cubed means there's 3 3's. So in total, you've got 1, 2, 3, 4, 5 3's. It's 3 to the power 5, which is no coincidence. 3 to the power 5 is 3 to the power 2 plus 3. There's a similar rule when you've got different bases but the same exponent. So x to the power a times y to the power a gives you x times y all to the power a. Here's a proof. 3 cubed times 4 cubed. So there's 3 cubed, there's 4 cubed. And if you take all those and multiply them out, you'll get 3 times 4 times 3 times 4 times 3 times 4. In other words, 12 times 12 times 12, or 12 cubed. So 3 times 4 is 12. You got x times y all cubed. There are quotient rules. If you've got the same base, as you can imagine, the x to the power a divided by x to the power b gives you x to the power a minus b. For example, 4 to the power 5, 5 fours, divided by 4 to the power 3, 3 fours. So if you cancel that 1, 2, 3, that cancels out 1, 2, 3 of those. You're left with 2 fours, which is 4 squared. 5 minus 3, that gives you those two exponents subtracted from each other, gives you the new exponent. As you might have guessed, there's also a quotient rule when you have the same exponent. X to the power a divided by y to the power a is x divided by y all to the power a. Here's an example. 3 lots of 4 divided by 3 lots of 2. So divide each one out, you get 2 times 2 times 2, 2 to the power 3. That's 4 divided by 2 is 2, and we've kept the cube exponent. It does get even more complicated though. So here's the first power rule. If you've got x to the power a, then to the power b, that's the same as x to the power ab. The a and b are just multiplied together. That's what we saw earlier when the square root was squared. That's why they cancelled out. The second power rule, also known as the power tower, is x to the power a to the power b. And the correct way to interpret that is to put brackets around the a to the power b. So you do a to the power b first, and that's the power of x you're looking for. And you can arrive at huge numbers using the power tower. Google is named after a power tower, for example. There is the third power rule, also known as the radical power rule. So if you've got x to the power a slash b, or a divided by b, in other words, a fractional exponent, that's the same as a root, which is the bth root of x to the power a. So this is why squaring is the inverse of the square root, because if you've got x to the power of a half, then the 2 goes on the radix, and the 1 goes on the power inside the radix, which of course just disappears and you get square root of x. So x to the power half is square root of x, and x to the power half to the power 2, they cancel out and you just get x. You can also have negative exponents. I think I might take a little short detour here to illustrate why this is the case. Let's make the font a bit bigger. So if you got something like x to the power 4, as we just established, that's x times itself, and it appears 4 times in that equation. If you get x to the power 3, then that's 3 x's that appear in the equation. If you got x to the power 2, that's 2 x's that appear. X to the power 1 is just 1x. When you get x to the power 0, no x's appear. But what actually is happening then is, if you multiply anything by 1, you get the same number you started with. So we could insert a 1 times at the start here. And that's really what's going on. You can see each time the power goes down, we're removing an x. We're dividing by x each time the power goes down. So remove that or divide by x, and you're just left with the 1. So anything to the power 0, with the possible exception of 0 itself, anything to the power 0 is 1. But when you get to a negative power, well, we saw a moment ago we're just dividing by x each time, so that would then be 1 divided by x. And x to the power minus 2 would be 1 divided by, I could draw divided by x, but that might get confusing, so I'll do it this way, x times x in brackets. So the number there still tells you how many x's appear, but if it's negative, then you're doing divisions rather than multiplications. So that's negative exponents. And 0 exponent, as we just said, is always 1. So that's the end of the elementary algebra section. We're going to look at Boolean algebra as well, and this is the last algebra, don't worry, that I'm looking at just now. This is named after Charles Boole, and it uses logic in place of numbers. So you get true and false values instead of symbols like 0, 1, 2, etc. Here's a typical programming example. A Boolean being declared called visible, so we're setting it to true instead of giving it a number value. So this is a Boolean data type that computers typically use. Or you can represent trues and falses as ones and zeros. This is called bitwise logic, and we'll see that shortly too. You get operators in Boolean algebra, just like regular algebra. And there's one here which is a unary operator. It just changes a true into a false or a false into a true. Now, it may use that symbol, which I don't actually know the name of, or the tilde symbol, or in computers it's often the exclamation point. So if you put exclamation point visible, what we're saying is if not visible. So we're taking the visible variable, let's call it A, and switching it to the opposite. So if A was false, it becomes true. If A was true, it becomes false. And this way of representing things is called a truth table. It shows you what output is true and which outputs are false. We've also got an operator called the AND operator, also called the conjunction. Symbols used there could be the caret, sometimes an X, a dot, an and, ampersand, sorry, or in the language I tend to use, it's double ampersand. So this is a binary operator. It takes two inputs, and the output, A and B, is only true if both inputs are true. The crappy sort of comparison or simile I always make is, let's say A is it raining? No, it's not. Yes, it is. B is, do you have an umbrella on you? No, I don't. Yes, I do. No, I don't. Yes, I do. If you combine these, A and B tells you whether to put the umbrella up. So if you don't have one, you can't put it up. If you have one but it's not raining, don't put it up. But if you have an umbrella and it's raining, you should put it up. Here's a Boolean OR operator, also called the disjunction. I don't know the name of that symbol either, but it's a reversed caret. Maybe that is its name, I don't know. It's sometimes also a plus, because it acts kind of like a plus sometimes in relative to algebra. A single bar, or the one I use, which is double bar. So this is another binary operator, combines two inputs, and the output is true if either of the both inputs are true. So if A is false, then the A or B is false. But if A is true, then A or B is true. And if B is true, then A or B is true. Or to put it another way, every output is true except the case where both the inputs are false. For example, imagine you're writing a game and there's two ways for your character to lose a life. So A is running out of time, B is hitting a bad guy. Do we lose a life? Well, it's A or B. Hit a bad guy, lose a life. Run out of time, lose a life. Do both, you only lose one life. You can't die twice at the same time, I guess. But if you haven't run out of time and you haven't hit a bad guy, you don't lose a life. One last one for now. There is more, as usual. But we're going to look at the XOR operator. This is the exclusive disjunction or exclusive OR operator. It uses that fancy plus inside a circle symbol, or a downwards caret with a bar underneath, or simply an X. There isn't an equivalent to this in C#, the language I'm programming in. But it's a binary operator that combines two Boolean inputs, and the output is true if and only if exactly one of the inputs is true. So if both the inputs are false, false output. One input's true, true output. Both inputs are true, then you get a false output. This is good for things like some one-time pad encryption, or flipping bits in a byte, that sort of thing. So then we're looking at Boolean operator priority. We've seen a bunch of operators in Boolean algebra. The order of operations is not entirely settled. This bit is more or less settled. You do brackets first. That's pretty much a given in any situation. We then do any not operators that might be there, any and operators, and finally any or operators. Notice what's missing. XOR. Now some people say it should come in here, third place. Some say fourth place. Some say fifth. It's one of those things that not all mathematicians agree on, and Boolean math is a fairly small field to start with. So as a result, I strongly recommend you use brackets quite liberally anytime there's any chance at all of any confusion. Okay, bitwise logic. In bitwise logic, a 0 represents false, typically, and a 1 represents true. So here's all the truth tables so far presented as bitwise equivalents. So if you get 1 or 1, you get the answer of 1, which looks a little bit weird, especially when you write OR as a plus symbol. You can say 1 plus 1 equals 1. I tend to think of it as numbers which are 0 and anything other than 0. So if you take A, which is 0, and B, which is 0, and add them together, 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. But there's the weird one. 1 plus 1 is 1. And like I said, if you try and think of this as zeros and not zeros. So if you take something that's not 0 and add something that's not 0, you get something that's not 0. With the AND operator, on the other hand, it does act very much like a multiplication. 0 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0, and 1 times 1 is 1. So you got a multiplication, you got something sort of resembling an addition, and then of course you've got the NOT operator. To round it all off then, we're going to look at bit masking, which is an application of these operators. So a mask adds or removes binary digits in specific locations. For example, you can mask out bits. You take this input, 10101010, and you mask it with this byte here, 00001111. I've highlighted those zeros because those are the bits which are going to be masked out. 0 and 1 is 0, 1 and 1 is 1. So this part here, because we've put ands with 1s, we get the same output. But if you AND with 0, you will always get a 0 because you need both inputs to be true for the output to be true. So this is masking those bits out. You're removing any data that might be there. You can also mask in data, and that is using an OR operation. If you OR things with a 1, so if you OR with a 0, first of all, then you get the same output. 0 or 0 is 0, 1 or 0 is 1. So OR with a 0, no change. OR with a 1, you're masking in a bit. It changes it to a 1 if it wasn't already. This masking out and masking in, you can flip individual bits in a byte, which is especially handy when dealing with ASCII/Unicode. You can change capitals to lowercase and vice versa by flipping a bit. You can change ASCII codes for 0 to 9 on the keyboard into the actual number 0 to 9 by flipping bits, and vice versa. And that's just one example. There's plenty of other uses once you dig deeper. But I think that's it for now. Speak to you later.